Before you get started on your own recording project, you should understand more about the basics of sound and how to control it. Even though computers have taken a lot of the work out of recording music, it still helps to understand the fundamentals of audio, which will help you become a better producer or a better engineer. And if you love the recording process as much as you do the music, you may want to think about working as a sound engineer. To do that, you'll need to understand a lot more about audio, how sound is produced, managed, and how it's recorded. In these videos, we'll talk about audio concepts related to recording and mixing audio without getting too technical about the science of sound. But you may want to learn more about these subjects yourself if you want to have a deeper understanding. Let's start at the beginning before sound gets turned into an electronic signal. When a voice or an acoustic instrument makes a sound, it's creating a vibration in the air. These vibrations come in waves of sound pressure. Faster or more frequent vibrations create shorter sound waves, while slower, less frequent vibrations create longer sound waves. When those waves hit our eardrums, we perceive them as sound. The longer sound waves with low frequency vibrations are heard as bass, while the shorter, high frequency waves are perceived as treble. As those air vibrations rise in frequency, our ears respond to the rise in tone. We can immediately recognize the difference between, say, the low-end rumble of a kick drum and the high-end sizzle of a cymbal. When a simple sound's vibrations have a very steady frequency that stays consistent over time, we hear that as a musical note. In music, we say that that note has a pitch. When musical notes vibrate at different rates, we say each one has a different pitch, and we give each pitch a name. But it's important to remember that frequency and pitch are not exactly the same things. The frequency of a sound can have an unlimited number of values, for example, and these values can be measured very precisely. Pitch, on the other hand, is a subjective human concept that people may disagree on. Different societies have defined pitch in different ways. For example, all the music that most of us listen to is based on 12 notes or pitches that we have chosen over centuries, even though we have an unlimited number of vibrations to choose from. In the late 19th century, inventors began to work on converting sound into a corresponding electrical signal. Experiments with different materials led to the first carbon microphones, which then led to ribbon mics and condenser mics that we still use today. We'll be looking at microphones more closely in the next series of videos. Throughout the 20th century, scientists improved the ability to capture sound and store it. We went from the cylinder reproducers of Thomas Edison to gramophones, phonographs, and reel-to-reel tape recorders. With the development of high-fidelity audio and sound systems in the middle of the century, we finally had the ability to record, play back, and hear sound that matched or even sounded better than the original. And digital audio lets us generate and shape sounds in ways we could never imagine. When we break down an audio signal, we find several characteristics that we need to understand in order to make great recordings. An audio signal is sound converted into an electrical voltage. A modern audio signal can carry all the frequencies within the full range of human hearing. These frequencies are measured by a unit called hertz, which is equal to 1 cycle per second. We use the hertz to measure many things in audio, from the pitch of musical notes to the frequencies that make up bass and treble, to even the speed that your computer runs at. Human beings can hear sound within a range of about 20 hertz, the very lowest notes and tones, to about 20,000 hertz or 20 kilohertz, the highest notes and tones. In music, notes have specific frequencies. For example, the A above middle C on the piano has a frequency of 440 hertz, or A440. In audio recording, a sound's tone is shaped by an equalizer or the EQ section of a mixing board. In a typical breakdown of tonal frequencies, the bass is from 20 Hz to 160 Hz, the mid-range from 160 to 1280, and the treble from 1280 to 20,000 or 20 kilohertz. Mixing boards and software equalizers will let you boost or cut the level of specific frequency ranges within a sound so that you can change its tone. We'll discuss this more in the videos on equalization. How accurately a piece of gear can reproduce a sound is called its frequency response. Ideally, every piece of gear would reproduce sound with no changes at any point in the frequency range. A graph of that condition would show a straight horizontal line from 20 Hz to 20 kHz, and we would say that that gear has a completely flat frequency response. Inside your computer, this is possible today with digitized audio. But in the analog world, this is not possible, so it's important to know the frequency response of microphones, mixers, amplifiers, speakers, and any other gear that handles analog audio. Every piece of gear will boost or cut the level of certain frequencies in the audio signal. On a graph, the result of this effect is called the frequency response curve. High-quality analog gear will have very minor fluctuations in this curve and exhibit a nearly flat frequency response. Changes of level in an audio signal are measured in units called decibels, which use the abbreviation dB. Both electronic and air pressure levels are measured in dBs. You'll see different flavors of dBs, such as dBm or dBu. These use different electrical voltages as reference points. In recording, you'll mainly just want to know whether one level is hotter than another, regardless of the electrical basis. For example, the most important level for our purposes is the record level, the strength of the signal you're recording to your storage medium. When recording was all done on analog tape, the record level was very critical because the signal needed to be hot enough to cover up the hiss created by tape running over metal heads, yet not too strong to overdrive the recorder's circuitry, which would result in distortion. The best record level in those situations might be, for example, around -3 or -6 dB, depending upon the tape machine and how it was set up. Using a negative value for your target record level meant that you still had a safety zone called headroom for sudden peaks in the signal, like the hit of a snare drum, that could drive the level up to 0 dB and still not distort. With digital recording, tape hiss and other sounds that make up the noise floor are not an issue, so there's lots of headroom to work with. But distortion is an even bigger concern because digital distortion is never pleasing, as small amounts of distortion can be in the analog world. So the standard digital record level is listed around -10 dB, more than strong enough to capture the original signal while staying away from the 0 point and digital distortion.